Hello everyone, I hope that you are doing well. So today, here in Statics of Rigid Bodies, we're now going to proceed to our third lesson, which is the moment of a force. So for this topic, we will have the following intended learning outcomes. So the first one is students should be able to recite the concept of moment. And the second one is to compute the moment of force systems. So let's start. Okay, so before we proceed to the definition of moment, let us first talk about why we need to study the concept of moment. So we need to study the concept of moment because we're going to use this, okay, to our succeeding topics, which are the resultant of parallel force system and resultant of non-concurrent force system. So we're going to need this concept in solving for those resultants. Okay, so the moment of a force, by definition, about an axis or line, is the measure of its ability to produce turning, twisting, or rotation about the axis. Okay, so let's say we have here a knot. Okay, let's say we need to loosen up this knot. Okay, so of course we're going to use a tool. Okay, so this tool is called a wrench. Okay, so we're going to need to apply a force in order to rotate this tool, right? So we have to apply, let's say, this force. Now, the measure of the force or the rotation of the force about this knot is actually measured in terms of moment. So that's how you measure, okay, the magnitude of the rotation of that force. So we measure it in terms of moment. So that's how simple, no, to define, okay, a moment. Okay. Okay, so let's proceed here. So the magnitude of the moment of a force about an axis which is perpendicular to a plane containing the line of action of the force is defined as the product of the force and the perpendicular distance from the axis to the line of action of the force. So let's say we have here a force. So this is in three-dimensional. Okay, so this force, if we want to measure its moment, we will need a reference axis. Okay, so let's say here, the axis that will serve as our reference will be the y-axis. So this y-axis will serve as the reference axis, okay, in measuring the moment of this force. Okay, so the moment of this force, okay, will be the product of this force and the perpendicular distance from the axis. So in this case, the perpendicular distance from the y-axis will be this distance. Okay, so this distance d and the force F, that will now be the magnitude, okay, of the force F about this axis. Now, if we are in two-dimensional, okay, so let's say we have this same force and this y-axis and this point O, no? So this y-axis, okay, if it's in two-dimensional, it will no longer be an axis. So if we look at its top view, no, for this illustration, so this axis, okay, this y-axis will now be a point now here in two dimensions, right? So this will be the point O and this will be this force. Okay, so in two-dimensional, if we want to measure a moment of a force, okay, so instead of an axis, okay, what we need here is a point, okay, to measure the moment of a force. So from here, okay, so we need also a perpendicular distance from that point, okay, to the line of action of your force. Okay, so line of action means the line where your force is applied. Okay, so take note, it's not just a distance, okay, it is a perpendicular distance. So meaning to say that distance, okay, should be perpendicular to the line of action of the force. Okay, so if we want to measure the moment of this force about point O, it can be written as M sub O, wherein this subscription is the point, okay, where we are getting the moment. So in this case, we want to find the moment of this force about point O. So that's why it is moment at point O, okay, is equal to force. Okay, so this is the force and the perpendicular distance. Okay, and also, um, we need to be able to analyze, okay, the perpendicular distance of the force, of the line of action of the force from point O, because that's what we need, okay, in solving for moment. So here, if we have a force here, so this is actually inclined already. Okay, so from this point, we know that its perpendicular distance is this distance, right? So this is where this distance will become perpendicular to this to the line of action of this force, right? Okay, and also let's say we have here this force. Okay, so and we want to solve its moment about this point O. So the perpendicular distance of this force, of the line of action of this force to the point O, will be this distance. So this is where it will have a perpendicular distance, right? And also, let's say we have here this force, and we want to measure its rotation or its moment, okay, about this point. Okay, so as you can see here, there's no perpendicular distance if we connect it this way or this way, right? So its perpendicular distance actually won't touch the force, but it's okay, because we can also extend the line of action of this force. So extending the line of action of this force, so extending it this way, so the perpendicular distance will be located here, somewhere here, right? So this will be the perpendicular distance. And also, in solving for moment, we also need to distinguish, okay, the rotation of a moment, okay, since it is rotation. Okay, so we need to know the direction. So we have two direction for moment or for rotation. So that is clockwise and that is counterclockwise. So those are the two directions for moment, clockwise and counterclockwise. So clockwise directions, of course, this is the direction, okay, of the hand of your clock, right? So that's how the hand of your clock rotates. Okay, and the counterclockwise is the opposite of that direction. Okay, so from these illustrations, these three illustrations, so this force actually has a clockwise, no, clockwise rotation about point A. So this force also has clockwise rotation or moment about this point O. And this force, okay, this force, its rotation or moment about this point O will be counterclockwise, right? So it's important that you know how to distinguish between clockwise and counterclockwise. So this is also a concept for moment. So the moment is equal to twice the area of the triangle formed by joining the center of moment with the ends of the force. So the center of moment that we are referring here is the point where we get the moment. Okay, so that is the reference point. Okay, so that's where we measure, okay, the moment of a force. So that is called center of moment. So the point O that we were talking about in the previous slide is actually called the center of moment. Okay, so again here, okay, so if we're going to illustrate what is said here, okay, so the moment is equal to twice the area of the triangle formed by joining the center of moment with the ends of the force. So let's say we have this force and we have this center of moment O or point O. Okay, so as mentioned here, that the moment of this force, okay, is twice the area of the triangle formed by joining the center of moment, by joining this center of moment to or with the ends of the force. So the ends of the force is this point and this point. So there will be a triangle formed here. Okay, so this will be this triangle. Now, if we're going to solve for the area of this triangle, so it will be one half, okay, of the base and height, okay, of the product of one half times the product of base and height, or one half BH, right? So that's how you solve the area of triangle. Okay, so here the base will be F. Now the height of this triangle, let's say the height will be this perpendicular distance, right? So this perpendicular distance will be the height of this triangle, right? So the area now for this triangle, okay, will just be one half F, okay, times d. Now the twice, okay, of that quantity as mentioned in this definition or concept will be the moment of point O of the force about point O. So here, as we can see here, so this 1/2 and 2 will just be cancelled, right? So what will remain here is just F times D, wherein your F times D is actually the moment of your force about point O, right? So this point, this perpendicular, this distance D is actually the perpendicular distance, right, from point O to the line of action of this force. So if you're going to solve for the moment of this force about point O, it will just be F times its perpendicular distance, which is this distance D. So basically, the concept here that is mentioned, okay, is actually proven right here, right? That the moment of point O, or the moment of a force about point O is equal to F times D. Okay, so this is just a concept. So now let's talk about one of the principles that we're going to use for moment. So one of those principles will be the Varignons Theorem. Okay, so we're going to use this principle often, okay, here in our course. Okay, so this is called Varignons Theorem. So its definition, so Varignons Theorem, the moment of a force is equivalent to the summation of moment of its components. So let's say we have here force R, okay, and we have here a point O. Okay, so this force R, if you want to measure its moment about point O, so it will just be R times its perpendicular distance. So the perpendicular distance of this force R up to this point O will be this distance. So this is the perpendicular distance. So this is perpendicular distance D. Okay, so that will be the moment at point O, R times D. And that moment is also actually equivalent, okay, to the summation of the moment of the components of force R. So in this case, since this is force R, its components will be this component, which is the vertical component, no, and this horizontal component. So these are the components of this force R. And these components, okay, let's say this force Rx or component force Rx, this also has a moment about point O. So if you want to solve for the moment of this horizontal component of force R, its perpendicular distance will be this distance. So this is, we name it here as distance 2, no? So that will be the perpendicular distance of this horizontal force. Now, also your vertical component, okay, of force R, okay, so this can also have a moment about point O. So we just need to have a perpendicular distance. So extending the line of action of that vertical component, so its perpendicular distance will be this way from point O. So the summation, okay, of these component forces is also equivalent to the moment of this force R. Okay, and also class, it's important to know that in summing up the moments of forces, okay, so we also need to use sign conventions here. Okay, so for moments that are clockwise, okay, so let's say the rotation of your moment is clockwise, so our sign convention for that is positive. Okay, so for counterclockwise rotation, meanwhile, it will be negative. Okay, so we will need this sign convention in summing up moments, okay, of forces. So again, Varignons theorem, okay, it states that the moment of a force, so this force, okay, so force R, its moment is RD. It is also equivalent to the summation, okay, of the moments, okay, of its components. So the moment of component Rx, or this force Rx, will be Rx times d sub 2, right? So since that is a clockwise rotation about point O, so that will be clockwise, right? Clockwise. So that will be positive. And your Ry, okay, so the moment of your Ry will be here times its perpendicular distance from point O. So that will be Ry times d1. And it is positive here since its rotation about point O will be clockwise. Okay, so this will be the summation, okay, of the moment of the components of force R. So this is the Varignons Theorem. Okay, so we're going to need this concept, okay, all throughout this topic. So also, this is another principle that we're going to use frequently here in our course for moment. No, so this is the principle of transmissibility. So principle of transmissibility states that the effect of an external force on a rigid body remains unchanged if that force is moved along its line of action. So it is said here that if we have a force and if we transfer that force, but we transfer it along the line of action of that force, so the moment of that force remains unchanged. Okay, with the same center of moment. Okay, so let's say we have here force F. So we have here force F, and we have here point O. So as we know that the moment of this force, okay, from point O will just be force times its perpendicular distance d. Now, let's say the line of action of this force will be the this extended line of actions, right? So if we're going to transfer this force F, this same force F, let's say to this position, so this force F, let's say it's also equal to F1, no? So so this is the same force, okay? So we just transfer it along the line of action of this force, no? So if we're going to solve for the moment of this force about point O, about that same point, so it will just give you the same moment, right? It will just give you also F times its perpendicular distance, wherein its perpendicular distance will be, if you extend this line of action, so this will be the same perpendicular distance d. So meaning to say, even if you transfer this force, as long as you transfer it along its line of action, whether here or here, it will just give you the same moment. So the moment remains unchanged. Okay, the effect of that force remains unchanged for the body. So that's the principle of transmissibility. Okay, so let's say we have here the illustration that we used from our previous slide. So let's say we have here force R. Okay, so this force R, okay, has this component forces, right? And its line of action will be the line where this force R is applied, okay? And its moment is will be R times D, right? So if we're going to transfer, okay, this force R, okay, let's say we transfer it here, but the place where we transfer this point, this force R is actually along the line of action of that force R, right? So this force R, even if we transfer it in this position, if we solve for its moment, okay, about point O, it will give you the same answer. It will give you the same magnitude of moment. Okay, so meaning to say, your component forces can be placed also here, right? So if you're going to solve for the moment of this component forces, it's also equal if you solve the moment of these component forces, okay, positioned here. Okay, so that's how the principle of transmissibility works. Okay, so we can transfer, okay, your force and your component forces, okay, as long as you transfer it, okay, along the line of action of the force, it will remain unchanged. Okay, so we're going to use this principle, okay, frequently for our course, ha? So you have to really understand this principle. So now let's talk about the conditions for zero moment. So these are the cases that the magnitude of your moment will be zero. So the first one, so a moment of a force becomes zero if either the first one is if the center of moment is on the action line of the force. So that is distance, or the perpendicular distance d is zero. Okay, so let's say we have here this force. Okay, so let's say we have here this force and we have here this point C. Okay, so if we want to solve the moment of this force. So by the way, this force, the line of action of this force passes through point C. So if we want to solve for the moment of this force about point C, as you can recall, your formula will be the magnitude of your force times perpendicular distance d. So but here, there will be no perpendicular distance since the line of action of your force will pass through the center of moment. So meaning to say the distance d or the perpendicular distance d will just be 0. So therefore, your moment, the moment of this force about point C will just be 0. Okay, so that's the first condition for a 0 moment. And also, if the magnitude of the force is 0, of course, if your force is 0, okay, even if you have a perpendicular distance, again, your formula is moments equal to force times d. So if your force is 0, so that will just give you a 0 moment. So these are the cases that the magnitude of your moments are 0. Hi, so this is a commercial. So this commercial is brought to you by Nescafe. Joke lang. So that's a joke. So this is for a bonus point. Okay, so what you're going to do here is just comment here in the comment section of this YouTube video. Okay, so you just have to comment your name, okay, your name, your section, and your answer. So for the following figures, okay, so you just have to indicate the rotation, whether clockwise or counterclockwise. Okay, so the first one is a clock. Okay, so what is the rotation of the clock? So that will be number 1. Okay, in your comment here below, you have to include also the item number, okay, of your answer. So again, your comment here should include your name, your section, okay, the item number that you answered, and of course your answer. Okay, so the first one is a clock, the second one is earth, okay, the third one is Ferris wheel, and the last one is Saraji's ikot-ikot dance. So what is the rotation of Saraji's ikot-ikot dance? So you just have to comment down below. So I hope you get the bonus point. So the first one, okay, the first to answer or to give the correct answer for every item will get the bonus point for every section. So I hope you get the bonus point. Bye-bye! So that concludes the discussion about concept of moment of a force. So see to it that you really learn this before proceeding to solving sample problems. Okay? Bye-bye.